In this video we're going to look at the standard solution method for linear second order differential equations. These are the examples taken from the textbook and we're going to solve the second of these. So our equation takes the form d squared y dx squared minus 10 dy dx plus 21y equals 0. We're going to look for a solution of the form y equals c e to the lambda x, where c is an arbitrary constant. Now substituting this into our equation, we have lambda squared c e to the lambda x minus 10 c e to the lambda x plus 21 c e to the lambda x equals 0. Provided the c e to the lambda x is non-zero, we can cancel that, giving us our characteristic equation, which is lambda squared minus 10 lambda plus 21 equals 0. And we can solve that. We can get the roots of that. We get lambda minus 7 multiplied by lambda minus 3 equals 0. So the roots are 7 and 3. Now that means that we can write the solution of this in the form y equals c1e to the 7x, or we can write y equals c2e to the 3x. And by the principle of superposition, if either of these solutions is correct, or both of these solutions is correct, then the sum of these solutions is also a solution. So we have y equals c1e to the 7x plus c 2e to the 3x. That's a general solution for this equation. Now, in order to solve for a particular solution, we need initial conditions, and these are some examples taken from the textbook where we're given initial conditions. We're going to solve the first of these. The first stage is to find our general solution. So we take the characteristic equation, which in this case is 8 lambda squared plus 6 lambda plus 1 equals 0. We can solve that using the standard quadratic formula. So lambda equals minus 6 plus or minus the root of 36 minus 32 over 16. And that gives us solutions minus a quarter and minus a half. So that means that we can write the general solution here using these roots. So we can write y equals c1 e to the minus a quarter x plus c2 e to the minus a half x. Now we want to use the initial conditions to eliminate these constants of integration. So to do that, we first of all need to take the derivative of our general solution, which gives us dy dx equals minus a quarter c1 e to the minus a quarter x minus a half multiplied by c2 e to the minus a half x, and we can now use our initial conditions, which are both evaluated at x equals 0. From the first we have c1 plus c2 equals equals 2, and from the second we have minus a quarter c1 minus a half c2 is equal to 0. We can solve this as a pair of simultaneous equations in c1 and c2, and we get a solution c1 equals 4 and c2 equals minus 2. And we can now use these to eliminate the constants of integration to get our particular solution, which takes the form y equals 4 e to the minus a quarter x minus 2 e to the minus a half x.